Welcome to Section 1.5, Exploring Angle Pairs. Last section, we dealt with angles in isolation. This section, we will largely be covering some special pairs of angles. First, we have adjacent angles. Adjacent means next to something, and that's good, since adjacent angles are angles that are next to each other. But mathematically, we have to be a little more specific. Let's look at some examples. Here we have a lovely example of adjacent angles. Angle 1 and angle 2 clearly look like they are right next to each other, and mathematically they are adjacent, so that's great. But that's the easiest one. Now it's time to play your favorite game and mine. Does this count? Here we have angle 3 and angle 4. This couple has only been dating a little while, and they aren't nearly as cuddly as our first couple. They only touch at a single point, giving each other a cute little peck. However, because they are touching at that single point, they are next to each other. At least a little. So this begs the same question. Does this count? Are these angles adjacent? I'll let you think about that for a sec. Let's look at another possibility. Here we have angle 5 and 6. They look a little more like angle 1 and 2. They touch at more than a single point, but they are offset a little bit compared to angle 1 and angle 2. But they still are touching, and therefore next to each other. So, does this count? Are these angles mathematically adjacent? Let's look at one final case. Here we have angle AOB and angle AOC. This time, one angle is inside of the other angle, but they do share that common side. So is this considered adjacent? Does this count? It was so much easier with angle 1 and angle 2, which are clearly adjacent. Are you ready for the answers? Have you come up with your gut feelings about which ones are adjacent and which ones are not? Let's see the answers. Angle 3 and angle 4 are not adjacent. You are not allowed to touch at a single point. You must have more. Angle 5 and angle 6 are not adjacent either. They do touch more than angle 3 and angle 4, but it's still not enough. You are also not allowed to have one angle inside the other. They have to be next to each other, not inside. Which brings us to this definition. Adjacent angles must share both a vertex and have a common side, but not have one angle inside the other. That's a lot of wording, but in general, adjacent angles just need to look like angle 1 and angle 2, which brings us to the definition. Adjacent angles must share both a vertex and have a common side, but not have one angle inside the other. That's a lot of wording, but in general, adjacent angles just need to look like angle 1 and angle 2. No deviations, however slight, are allowed. Now we move on to another special and very useful pair of angles. Vertical angles. At least that is what we call them in the US. In many parts of the world, they are known as vertically opposite angles, which is actually a bit more descriptive of what they are, but we will be calling them vertical angles for this course. In order to create vertical angles, you need two intersecting lines, like this. With these intersecting lines, we create four angles, like I have numbered here. For now, we will ignore any straight angles. So let's look a little closer at those four angles. We need to focus on the opposite angles when two lines intersect. In this picture here, angle 1 and angle 3 are vertical angles. Similarly, angle 2 and angle 4 are vertical angles. The official definition of vertical angles talks about a pair of angles whose sides are opposite rays, which is fine and all, but the definition feels unnecessarily complicated. Most students are more comfortable thinking about vertical angles being on opposite sides when two lines cross. Some more examples. Once again, they are color-coded to make it easier. Angle 5 and angle 7 are vertical angles. Angle 6 and angle 8 are vertical angles. Angle 9 and angle 11 are vertical angles. Angle 10 and angle 12 are vertical angles. You should be pretty comfortable identifying them by now, which is good. They come up a lot. You absolutely need to get them down. Now a quick word about the misleading name. Angle 1 and angle 3 seem to be clearly what most would think of as vertical. But what about angle 2 and angle 4? Are those horizontal angles? And what do we do with angles 10 and 12? Are those diagonally slanty angles? To understand the confusing name, you need to know that when they were coming up with a name for this concept, they derived the name from the fact that these angles share a vertex. The same root is used for both vertex and vertical. Today, vertical almost always is associated with an orientation, which leads to the confusion about the name. In truth, it was originally supposed to refer to the shared vertex and had nothing to do with the orientation. Now we come to the first geometry word which people continuously misspell. The way I have spelled it here is not the way it is spelled if you are talking about the geometry word complementary. However, it is the way a lot of people will spell it. If you do spell it this way, with an I in there, then what you are talking about is this. These are examples of complementary angles, spelled this way with an I. They are giving out nice, okay, maybe let's go with cheesy, complements. So now let's change it to the way it should be spelled. That's better. Now complementary with an E is a whole different beast. One letter makes quite a bit of difference. Complementary angles are two angles which add up to 90 degrees. Like this. Since these two angles are complements, we can also say the 51-degree angle is a complement of the 39-degree angle, while the 39-degree angle is a complement of the 51-degree angle. It's just a different way to talk about the same idea. What happens if I do this instead? Does this picture depict complementary angles? Put all three angles together and you get a right angle. So does this work? To get your answer, you need to carefully look at the definition of complementary again. The definition clearly mentions two angles. So it can't be three angles. It must be only two. That's why this doesn't work. So what about this? Do these count as complementary? Are you allowed to have angles not next to each other? This is okay. The definition doesn't say anything about how the two angles are situated or oriented. All it says is that there are two angles, and those two angles add up to 90 degrees, no matter where those angles are found. Now we get to supplementary angles. Supplementary angles are just like complementary angles, except instead of adding up to 90 degrees, they add up to 180 degrees. Just like complementary angles, once we determine that we do have supplementary angles, then we can say this. The 109-degree angle is a supplement of the 71-degree angle, or the 71-degree angle is a supplement of the 109-degree angle. Note that the definition of supplementary specifically says two angles, so just like the complementary ones, you can't have three or more angles that add up to 180 degrees. Also, it doesn't mention location again. So it is fine if the two angles are not together. As long as you're only talking about two angles, and they add up to 180 degrees, then that's all you need in order to say they are supplementary. Complementary and supplementary are not tough concepts, and generally students get the idea pretty quickly. But there is one thing which constantly trips them up, remembering which is which. Which one is 90 degrees? Which one is 180 degrees? If I hand out a quiz or a test with these concepts, you can sometimes see a student mentally flipping a coin in their head to see which way they are going to go. I'm not going to tell you how you have to remember which is which. That is up to you. However, this is the most popular method by far. Just like the letter C is before the letter S alphabetically, 90 is before 180. If that is good for you, great. If you want to remember it some other way, that is fine too. It is up to you, but it is by far the most common error students make with complementary and supplementary. Speaking of supplementary, linear pairs are very similar to supplementary except one change. Although, by looking at that definition, you wouldn't know it. When I see a definition like that, I just shake my head and sigh. That should be a clue I won't be expecting you to spit that definition back out to me. It's ridiculous. A linear pair is a really simple concept, and it is unnecessary to make it sound so complicated. A linear pair is simply a pair of adjacent angles that together form a straight line. So let's switch what's on screen. Just like supplementary, we are talking about two angles only. Just like supplementary, the two angles add up to 180 degrees. So the picture I used from the supplementary section works here too. These two angles are a linear pair. But the definition of a linear pair also mentions adjacent. That's the one tiny change, which leads us to this distinction. The two angles on left are both supplementary and a linear pair. The two angles on the right are supplementary, but since they are not adjacent, they are not a linear pair. A linear pair, like the name implies, forms a line. You absolutely need to know the difference between supplementary and a linear pair. Now I just told you that two adjacent supplementary angles are known as a linear pair to get the concept across. On this slide I show you the concept written out as a postulate. Like most postulates, this should seem like common sense. Obviously, if two angles together form a straight line, or a straight angle, then they would be supplementary. Well, duh. Angle bisector is next up to the plate. We already did a segment bisector, which is something that cuts a line segment in half. So an angle bisector is something that, yes, an angle bisector is something that cuts an angle in half. Pretty simple. So below I have a lovely 78-degree angle. Let's show an angle bisector in action. Now the angle has been chopped into two congruent halves. That's what an angle bisector does. That's it. No need to overcomplicate it. Now we need to lay down some ground rules for how we will proceed through the rest of this course. There are some things that you are allowed to assume, and some things that you are absolutely not allowed to assume. Let's go through them. First, what can we assume? We are allowed to assume that angles that look adjacent in the picture are actually adjacent. It would be pretty evil to say that it's possible that an impossibly thin gap is between those two angles, and it screws up everything you are trying to do. So if two angles look like they are next to each other, you can assume that they are. This would be completely ridiculous. I would make geometry absolutely impossible. If you couldn't assume something was actually straight, then you'd be toast. That's the official term. You are allowed to assume that two angles form a linear pair. Here these two angles look like they form a straight line. That's fine. Just like you can assume lines are straight, you can also assume that two angles that look like they form a straight line actually do. Lastly, you are allowed to assume that angles that look vertical really are. You might see a theme going on here. This also follows the line of thinking that you're allowed to assume lines are straight, and thus form vertical angles. That's the bottom line. You can assume lines are straight if they look straight. Now what we are not allowed to assume. You cannot assume that angles or line segments are congruent. Even if you take out a protractor and measure the angles and determine that they are the same measurement, you still can't assume they are congruent. Even if you take a ruler out and measure the bottom line segments to see they are the same measure, you are still not allowed to say they are congruent. So measuring is out. Unless there are some markings on the picture to say they are congruent, or you can figure it out by other means, do not assume they are congruent. It gets students in trouble all the time. Did I mention students getting in trouble all the time? This is one of the most common ways. Students often will assume an angle is a right angle because it looks like it. Again, even if you pull out a protractor and measure, you still can't assume that it is a perfect measurement. Even if you lay something with a right angle, say a 3x5 card, and verify it looks 90 degrees, it still only looks 90 degrees, and you don't know for sure. Without some markings, measurements, or some way to figure it out without any gray area from the picture, you cannot assume something is a right angle. It is a very common mistake from geometry students. Lastly, you can't assume angles are complementary, especially when they are adjacent, like in this picture. Again, you should sense a theme. Assuming things are straight is fine, but assuming things are 90 degrees is not. Clearly, geometry teachers are biased against those blasted right angles.